join me to get this lovely background prepared by Dr. Ruppert. Um, Soils, hydrology, and nutrient retention on the eastern shore of Maryland. Preparation for the MAPSS tour tomorrow. Sounds like it's going to be a great day. So I'm going to turn it over to Dr. Ruppert.
Thank you very much. I want to thank you for making this possible and thank each of you for coming. Um, I look forward to spending the next hour with you. And I've you're going to be looking at the PowerPoint that I have. Um, that'll be up on your screens. I've sent you an electronic copy of the same PowerPoint. Um, I just sent one a few minutes ago because I found a couple typos. They're very minor and insignificant. Nonetheless, the main resource that I've provided with you, that I've provided you, is not the PowerPoint. It's the Word document. It has many of the symbols we're using, but it has some deeper explanations than we're going to have time to go into. I hope to get through all of the slides and even for us to even to get to a little video at the end of this, but we may not have time. And the Word document that I sent yesterday, you should really think of that as your primary resource here. I also want to say congrats to Emily, who will not be coming on our tour tomorrow because she's going to be flying to Chicago to go to Argonne National Laboratory to work over the weekend with no sleep at an at a X-ray source at a synchrotron. So and she's going to be basically analyzing soil samples gathered from some farms on the eastern shore with high phosphorus levels. And Emily will actually be able to see in what molecular form the phosphorus is and what it's sticking to minerals. So it's very exciting and obviously very high tech. And so we're really proud of her. And so I hope, Emily, you're going to have an absolutely wonderful weekend. Yeah. So thanks so much for joining. You might be wondering what MAPSS means. MAPSS means the Mid-Atlantic Association of Professional Soil Scientists. And you can see that there's another typo I actually missed. It shouldn't be MAPPS. It should be MAPSS. So in any event, thank God for recording so everyone can at least hear that and figure it out on their own. All right. So here's what we're going to talk about today. In order to be able to maximally enjoy tomorrow's tour, we want to be able to identify the different horizons we're going to see in the pits that we go to. We're going to want to be able to identify the most basic level of soil taxonomy that we see, which is the soil order. We're going to talk about how we identify soil texture. We're going to talk about how soil texture influences nutrient retention, how it influences hydrology, and how those textural differences will also prompt changes in soil layers over. So that's kind of interesting. But there's one thing we're going to go into. We are going to go into the depths of USDA soil taxonomy. So if you're wondering what a mixed mesic kaolinitic typical haplodelt is, that's not what we have time for today. Be able to understand the alt part, last part of that. All right. But don't worry, the preceding parts actually aren't that bad. And if we were to go through it, it would actually be far easier than you think. Okay? All right. Thanks for being here. So I've taken just a portion of the first in the Word document that I've given you. I've blotted out all the parts I want you to be paying any attention to. Right now, with what you're seeing, I want you to be able to take this and to be able to identify what soil scientists refer to as a sea horizon. All right. And it's so easy to identify a sea horizon typically, because what we're looking for with a sea horizon is we want to look at how the soil particles are arranged. If it looks to us like they are arranged exactly the same way that they were deposited there by Mother Nature, So for example, with a river, if it looks like the material is still reflected in kind of its river position or its marine deposition, then the structure of the material hasn't been altered yet. And by definition, it's going to be called a sea horizon. Okay? If it looks like it has structure that's developed in place since it was deposited because of a soil process, well, then it couldn't be a sea horizon. All right? Now, some of you are also aware, well, there are such things as R horizons in soils, and there's no doubt about it. But we're not going to see one tomorrow because R stands for consolidated rock. And that's there on the eastern shore, but it's about a mile below the surface. So, so we're simply not going to see it. We'll see rocks, but not rock that's consolidated in a mass. All right, so do you want to know what a sea horizon is? Distinguish whether the material that you're looking at has the structure as it was deposited as a sediment, or if it has structure that looks like it developed in place. And we will get better at observing that second type of structure very quickly. For the moment, though, let's just look at this slide that shows you two different sea horizons together. All right. Now, this is a this is a picture from Alaska, and so material in Alaska gets heaved a lot by freeze and thaw phenomenon. So I want you to ignore the fact that these horizons are no longer horizontal the way they would have been when they were first deposited. What I want you to pay attention to is that the lower one is looks like a riverine deposit, kind of like a cobble bar that you see in a river, where many of the particles are rounded and they're all about the same size. And then above that would be another riverine deposit, but clearly deposited when that stream was flowing at a much slower rate and was dropping off much smaller materials. You can still see kind of the laminar flow that dropped those things off. Ignore the fact that it's no longer horizontal. That's occurred because we had a kind of this heaving due to freeze and thaw. But what I want you to see here is that we really have structure that is really unchanged from the way it was originally deposited. Um, these two, like you will see in the Microsoft Word document, we are almost here dealing with two completely different parent materials. Um, in the one case, it's deposited in a kind of very slow moving regime, and the other, with the big cobbles, a much faster moving regime. And like you'll see elsewhere in the packet, and I won't mention it again, if we have two different parent materials in a soil, then in the new parent material, we stick a 2 in front of all those designations. Okay, so a couple sea horizons, from Alaska. But I'll tell you that on the eastern shore, depending on how fast the river was flowing that deposited those materials, we could get things that look like that. All right, structure unaltered by soil processes. Here's another shots of seas versus not sea. If you see where we've got the sea horizons labeled in these two soil profiles, there's really not a lot of structure there. It's essentially the same structure that was always there in place. Soil processes haven't changed it at all. But if you can see where I've labeled not sea, you can see that we've got some structure there that is different from what's at the very bottom. All right. It's a little bit more subtle to see in the red soil, but nonetheless, where you can see that we've got not sea, you can see that we have some vertical structure in that soil there that simply isn't observable further below. Interestingly enough, in the grayer soil to the left, you can see the similar vertical structure. Two completely different soils that have created the same structure over time, despite completely different parent materials, completely different weather, but they share a similar processes of development that have given them that soil structure that was never there in the first place. All right, so that's how we can distinguish sea horizons. We have sediment structure versus structure that's developed in place through soil formation. All right. Anything that's got structure that's developed in place through soil formation is going to be something other than a sea horizon. Well, let's talk about another type of horizon, one that has structure that's indicative of the fact that that structure developed in place as a soil occurs. All right, and typically in these next horizons called B horizons, what we're doing is we're accumulating something. Not in every case, but usually. Um, in most of the cases on the Eastern Shore, what we're doing in a B horizon is we're accumulating clay. And where is that clay coming from? It's accumulating in the B horizon because it's been moved out of horizons from above. So do you see above the B horizon, we have other horizons that are going to be leached, but the B horizon is the place where that leached material is collecting. And not only is that material collecting, but that B horizon has also developed its own unique structure, different from what was there in the first place with sediment. So now let's look at a couple of examples of B horizons. All right, well, we've seen them before now. All right, C horizons with little structure. We've got the B horizons where we've gained this structure that hadn't been there before, but we're also, it turns out, accumulating. Now, how would you know that stuff is accumulating from these pictures? There is absolutely no way for you to tell from these pictures that stuff is accumulating. I happen to have a little bit of experience with soils, and so I know beyond a shadow of a doubt, if we were to compare the different horizons above and below that B, we would see evidence of clays accumulating in those horizons there. But there's no way that you could know just from the picture itself. Okay? What we're going to be able to see in the data that we're presented tomorrow, that in fact, in these horizons that have uniquely developed structure, um, that the Mid-Atlantic Association of Professional Soil Scientists are calling B horizons, indeed, they are also accumulating something. And most typically, it's going to be clay. So in some cases, horizons are going to accumulate organic matter. And as from the table as it's developed, sometimes B horizons will accumulate organic matter, not just clay. And we're going to see examples of that in a second. Another type of horizon that doesn't have soil structure, it has structure that doesn't have sediment structure, it has structure that's developed in place. But it's characterized by leaching and not a place where organic matter is accumulated. So it has soil structure, but it's leached and accumulated anything. And that's an E horizon. E horizons are, we're going to see some tomorrow, I bet, but we're probably not going to see too many of them. So let's see what some E horizons look like. All right, well, here we've got a new soil profile. All right. We've got this the sediment structure below. We've got a zone of accumulation, right? That's some type of B horizon. And then above that, we've got a horizon that is lacking color. Why? Because leached from it. Has that E horizon that's had stuff leached from it, has it accumulated organic matter? All right. So the stuff, it might be leached, but it's accumulated organic matter, and that makes it not an E. All right. Now, one thing to note, chances are soil profiles that we see tomorrow, differences that I'm showing you in the pictures here will not be nearly as pictures that I'm showing you here I'm using because they show the differences so clearly. But in real life, these differences are far less clear. And sometimes we only observe them through the chemical data. All right. Now, hopefully, we'll go into some soils tomorrow where we'll just be able to see the whole picture from outside the pit. But I want you to know that that's rare. And so don't be frustrated by that when that doesn't happen. Okay. What about those horizons that we have that are zones of organic matter accumulation? Well, we can distinguish two types of soil horizons where organic matter is accumulating. In one case, like all the other horizons we've seen before, that horizon is mostly mineral, mostly sand, silt, and clay. It's got a little bit of organic matter, usually less than 5%. Nonetheless, that small amount of organic matter is enough to make it dark. All right. That type of horizon is called an A horizon. But there's of horizons where we have a lot of organic matter that is accumulated. So much so that that horizon feels almost 100% organic, even though it might not be. And in that case, we have what we call an O horizon. Let's look at some examples. So in this case, we've got a mostly mineral horizon um, at the very top. Because it might be accumulating organic matter, it's mostly mineral, and it's an A horizon. Now, how do we know that that's mostly mineral just from the picture? Well, the truth is we don't. I'm just banking on my experience looking at that to say that that's probably an A horizon. In order to really know, we'd have to do a lab test to actually see how much organic matter is there. Okay? So I don't want you to think that you should be magically able to look at a picture and be able to automatically know these things. I'm using a little bit of my my book learning to make some educated guesses. The truth is, for anyone to know, we can't really tell from a picture. We'd have to have the lab data. All right. But let's look at some examples of O horizons, or things that are really probably organic. In one case, we've just got the O horizon from the soil, and that's in another we've got an O horizon sitting over top of something else. And who do we know? How do we know what that other stuff is? Well, we can't really tell from the picture. We'd have to look at it. We'd have to see more of it. Does that make sense? Now, by the way, if you look at this picture on the left, you can see that the nature of the organic matter in this thing that's being held in the hand is actually different from top to bottom. You see it's a little bit less decayed near the top and more decayed near the bottom. So it turns out that you can split different horizons into different subtypes. All right. And that's what the right-hand side of the table is that I've provided you in the Word document. And that's what and indeed, the right-hand side of the table that we've got in front of us now. Do you see how there's different types of O horizons? It all depends on just how degraded the organic matter is. If it's not too degraded, like at the top of that little handful, well, we'd call it an OI. If it's so degraded that we can't even tell the origin of that organic matter from before, well, then we call it an OA. See that? We can also we can also designate different types of the other types of horizons, all right? If there's no subscript, then that means it's just kind of a generic garden variety type of that horizon. But sometimes there are subscripts that we use to indicate something that's important to understanding the soil. Look at all those subscripts. That means that those horizons have been turned a grayer color than the color in the original parent material. That while that material has been in place, because of soil processes, that those horizons have been stripped of their color and made gray. How does that happen? I've got it written up for you really nicely and tidily inside the Word document. But essentially what happens is that those horizons get seasonally saturated over many, many centuries. And during those periods of seasonal saturation, the bacteria that are resident there run out of oxygen to breathe, and they're forced to breathe something else, which is something that only bacteria. One of the things that bacteria can breathe, and only bacteria can breathe, is iron. And when they do that, they take the colorful oxidized form of iron, iron 3, and they turn it into the colorless, soluble form of iron, which is iron 2. So over the course of centuries, turning the rusty red, insoluble form of iron into the colorless, soluble form of iron allows the iron to leave. And so after many centuries, we can change the color of the soil because of seasonal saturation, because of bacteria. So also notice that we've also got a P subscript for A horizons, and that's because when soils are farmed or there's other human activity, we tend to disturb the soil surface a lot, and we can identify that with a little p. Here's a soil that would need a G subscript, right? G due to seasonal saturation. The water table soil likely goes to near the top of the soil frequently during during at least during some portions of the year. Here's a couple examples of where a P might get married. Oftentimes, we'll say that we have an AP horizon when that A horizon has a very abrupt bottom. In natural A horizon, the bottom of the A horizon is a little bit more diffuse or a little bit more wavy. But where that A horizon has a very abrupt bottom, oftentimes, and we think that it got that abrupt bottom as a sign of human activity, oftentimes plowing. Don't let P stand for plow, let P stand for people. But oftentimes the P comes from, if that bottom is very abrupt and we think that it's likely that that happened because of farming, then we'll call that, or because of human intervention, then we'll give it a P. The soil on the left, that boundary is obviously very clear. But if you look on the soil on the right, even though the color difference is subtle, you'll see that across the boundary from kind of the light brown into the reddish brown, you'll see that that change is very abrupt. In both cases, I think those would merit being called AP horizons. All right. So what we've done is we've gained the ability to make observations and good educated guesses about the nature of the soil horizons that might be in a pit that we're observing. And I want you to notice from this table that there are going to be different types of B horizons there, but there's so many that we couldn't put them here. And so they're going into this next table that we're going to look at. So how do we identify different types of B horizons in the mid-Atlantic? There are other types of B horizons that show up around the world, but these are the ones that we're typically going to see in the on the eastern shore. All right, and notice that it's always a story of accumulation, right? In one case, a W horizon is a B horizon that's in just beginning to form. It's inherited a soil structure different from the parent material, or it's a little bit redder, and that's about it. Something is beginning to happen, but the expression isn't very strong yet. But what if we're clearly accumulating clay? Well, we call that a BT horizon when that clay is leached from above. What if we're accumulating or well, we call that a BH horizon. If we're accumulating iron and aluminum, we call that a BS horizon. What, of course, if we've got a B horizon where we've lost color because of seasonal saturation? Well, then it gets a G subscript. And like it says in the Word document, sometimes you need more than one subscript to adequately say what's happening. Let's look at some examples. So if you're accumulating clay, accumulating a significant amount of clay, then that BT horizon can be called argillic. Chances are, if we were to look at the data from these soils, the amount of clay that's collecting in those BTs is several percentage points greater than what we find in the material above. We're not only calling these things BTs, but argillic BT. But you can also have what we call spodic horizons, and there's two different ways to do that. One is to accumulate aluminum oxides from above. That's what we call a BS horizon, a spodic BS. Or we can be accumulating organic matter that's leached from above. In this case, we have a spot pH. Sometimes we get both, as you can see in the soil profile to the in both of these cases, the leaching from above was so strong that it created an E horizon above. Not all soils will have E horizons. As you can see from these soils here, E horizons are not obvious. You can get an E horizon above a BT, but it can take a really long time for an E horizon noticeable to form. Spodic horizons as well take a really long time to form, on the order, in both cases, a BT or a spodic horizon, argillic BT or a spodic BT or BS or BH. We're talking thousands of years. Here's a BW horizon. You can see that it's got soil structure that's different from below. You can see that it's a little bit redder from what's below, but at the same time, it's not entirely clear what's happening there yet. All right, this is a more weakly formed B horizon. Another neat thing that we can do is we can say, okay, well, where are we likely to find types of B horizons? Well, think of a BG horizon. Where are we going to get seasonal saturation? Typically at lower places on the landscape where the perched water table. Clay isn't very soluble, um, and iron and aluminum aren't very soluble. They get a little bit more soluble in the presence of organic matter. So when are we going to get a well-developed BT or BS horizon? Only after a really long period. That's how you're going to find soils with BT or BS or BHS horizons, old soils. What about a BW horizon, a soil that's kind of a soil horizon that's just starting off? Well, we're going to find those in soils that are relatively new, that were probably disturbed not too long ago. An example of that would be in a floodplain, but a floodplain that isn't scoured or where new material isn't deposited that often. A floodplain that's basically stable, but that is still sufficiently active that it disrupts things from time to time and doesn't really allow a soil horizon to start forming for a very long time. Okay. So we've just ended our first effort, which is our ability to observe different horizons in soils. That's really most of what I wanted to talk to you about, or it's about half really about what I wanted to talk to you about today. Now let's get to the other half. The neat thing in USDA soil taxonomy is if you can identify certain characteristic horizons, then chances are you can identify the basic soil. Okay? And so that's what that this portion of this table is designed to teach you to it. Now notice there's a hierarchy here. USDA taxonomy wants us to look for certain horizons first. And if we find them, then move on, see if we find other horizons. The first time that we observe a horizon that's kind of in this table, well, then that automatically is going to dictate what type of soil we have. All right. So notice that soil taxonomy, USDA soil taxonomy, puts a huge premium on thick O horizons. If you've got one of those, it doesn't matter what else you have. It's automatically going to be a histosol. That soil could have spotted horizons, argillic horizons, everything, but if it's got thick O, it's going to be a histosol. No question. All right. But what if you're looking at a soil and there isn't a thick O horizon? Well, then the next thing we're going to do is we're going to look for the presence of a B horizon. And the question is that B horizon strongly expressed or poorly expressed? If it's strongly expressed, then what we do is look for the type of strongly expressed horizon. If it's got a spotted horizon, a BH or a BS horizon, or a combination of the two, then it doesn't matter what else is there. It will automatically be a spotosol. But what if it doesn't have a strongly spotted horizon? What if it's got a strongly expressed argillic horizon where clay has accumulated? And we can see that very clearly in the data, and we can feel the soil texture difference that it makes in a particular horizon. Well, then we've got one of two types. We have an ultisol or an alphasol. Um, Most of the soils in Maryland that have a strongly expressed argillic horizon are going to be ultisols. And all of the all of the soils on the eastern shore that have argillic horizons are basically going to have started out as ultisols. However, some of them have been artificially turned into alphasols. Here's the difference between the two. The difference between the two only has to do with chemistry. You guys know about cation exchange capacity. Well, there's a quantity related to cation exchange capacity called base saturation. Base saturation is the share of the cation exchange occupied by potassium calcium, magnesium, and sodium. And those are all relatively soluble um, ions. So typically on the eastern shore, these old soils that have been in place for a long time, they've really been washed out of the soil profile. There's not a lot of them. And ultisols are soil strong BT horizon and horizon that also don't have many of those bases. If we've been very diligent about liming for many, many decades, what we do, of course, is by liming, we're putting bases back in. And if we've done that often enough, for long enough, then we can take what originally started off by Mother Nature, ultisol, and we can make what we cultivated alpha sol. We can actually change the soil chemistry enough and increase the amount of calcium and magnesium in that soil. So the cation exchange capacity is primarily occupied by bases. So we get an alpha sol. The cutoff between an ultisol and alpha sol is a base saturation of 35%. So that's how they decided, and that's definitely going to be a talking point tomorrow as um, for the soils that we visit. Now, what if you do have a B horizon, but what if it's not strongly expressed? What if it's poorly expressed? Well, then it could be a B horizon of any type, a BT, a BH, or a BW. But if it's poorly expressed, we call it a cambic horizon, and then automatically, no questions asked, we have an inceptisol. And what happens if we have an O horizon, we don't have any B horizon at all? The only thing that we've got left is an entisol, all right? And that's a soil that's been in place for not very long. Not a lot has been able to happen soil development wise. And so we just have essentially usually A horizons over C horizons, all right? Now, the neat thing is that we can also, just like we can generalize about where in a landscape we're likely to find different types of B horizons, well, we can also generalize where in a landscape we're likely so these different types of soil orders. So where are we going to find a histosol, a thing with a thick O horizon? Well, look down here. You can see midway through the page, I've got various development factors. And if we look for histosols, look for parent materials, and you can see that what we've got to have for a histosol is we've got to have high addition of organic matter, but a low breakdown rate for organic matter. That's how we build up that O horizon, right? Plenty of additions of organic matter, but slow breakdown. And what situations do we get that? Well, we get in situations where we get that is where the water table is high, where the ability of microbes to break down the organic matter is limited because their oxygen has been excluded. So they break down organic matter slow, but there's plenty of water there for plants to grow, so we get plenty of it added. And what we end up doing over time, typically over the course of tens of years or hundreds of years, is we get that thick O horizon to develop, and we get a histosol in marshes. Now you can find an O horizon in a well-drained soil, but chances are the O horizon got there not because the soil was well drained, but because back in the day it wasn't. Remember that about half of our wetlands in the United States have been drained. Why? Because we love growing on those O horizons. Okay? So if you see an O horizon, that means that typically it's either seasonally wet or it was seasonally wet in the past before artificial drainage was imposed. How about getting a spotosol because of spodic horizons? Well, we need a large period of time. Typically, we only see them when the parent materials are sandy. Um, the We typically see them in a forest situation, and typically we have to see them under conifers. All right. If we've got sandy soil horizons, if we've got sandy horizons, sandy parent materials under coniferous forest, and if we can wait long, then we'll be seeing horizons and spotosols. When do we get an ultisol or an alphasol? And I can see here the very last type. I hope that I forgot to that I ultisols or alphasols. Unlike this table, what this table says, sols can form in any type of parent material, very sandy to very clayey. Let me see if I've propagated that mistake. No. So if you look on the Word document, that mistake isn't there. So again, the Word document is the primary material here for us today. All right. So unlike the table in front of you, but like the table in the Word document, alpha sols or ultisols can develop in any parent material, but typically they did develop under forest instead of coniferous forest, hardwood forests. And they develop over a long period of time. It takes a long time to move clay downwards. So what you can see is that most soils on the eastern shore, because it takes any parent material, it just needs to be stable for a long time. Developing under forest, we're going to get ultisols. And so most soils, most upland soils on the eastern shore are going to be ultisols originally. Some of them will have been changed by human activity into alpha sols. If we go to certain places in the landscape where that are periodically disturbed, so we could be talking about semi-active floodplains or a ditch that hasn't been dredged for a really long time, well then we can get the beginning of a B horizon and then an inceptisol, any type of parent material. Where are we going to find entosols? We're going to find entosols in places that are frequently disturbed. So those could be dunes. They could be a ditch that has recently been dredged, or a spoil pile that just got vegetated, or an active floodplain. So the neat thing is that you can think of where you are in the landscape and ask yourself, what kind of soils do I think I would have under, right? It's a nice intuition to develop. We are talking about soil texture. Yes, ma'am.
We have a question here. We're asking about if the O horizon is only in a wet area or that a thick horizon is present in a area slash previously wet area. So O horizon versus thick O horizon present in a wet area or previously wet area.
To get an O horizon, soil wetness really help. If you want to get a thick, and thank you for the question. Who has it? Thank you, Ashby. To get a thick O horizon, you really typically will need some wetness in order to minimize the breakdown rate of organic matter. Um, Another way to minimize the breakdown rate of organic matter is to be in a cooler climate, like you would have out in Western Maryland. So in places, especially out in Western Maryland, you can find O horizons that have developed not because of wetness, but because maybe the vegetation is from conifers. It's acidic. It's hard to break down anyway. The growing season is shorter, and so therefore the amount of time that a bacteria is warm enough for a bacteria or a fungus to break the material down is limited. So you can get O horizons outside of wetland situations. If you want a thick horizon, being in a wetland situation really helps. But even on the eastern shore, you can find O horizons. You just need to have enough organic matter accumulate. Now, you can make a distinction between what you might call just duff, which is kind of loose leaf material, versus actual soil material. And I think the difference that you would make that distinction by observing rootedness. If you've got organic materials and there's roots running through them, you can see that it's kind of clearly anchored in place and functioning as soil, then that's an O horizon there. If it's just loose organic material like fresh leaf fall, that's not yet soil. That needs to be stabilized before it's a functioning part of the soil, and we just call that duff. Make sense? Thank you for the question, Ashby. In the absence of another question, let's start talking about soil texture, okay? Now, this is something you guys already know. We can distinguish between sand, silt, and clay based on different sizes of the material. And then we can distinguish overall soil textures for material using a texture triangle. And I haven't included it on the slide, but one of the pages on the handout that I've provided, the Microsoft Word document, is the flow chart about how to hand texture based on different criteria. All right, so you've got that, and you're familiar with that from soils classes that you've had before. A lot of what I'm giving you here in this webinar is review anyway for those who have had a soils class. All right. Now, Why does soil texture matter? It matters for so many different reasons, but one of the reasons why it matters is because soil texture helps to decide chemical behavior. The so we've just got a reproduction of that table that distinguishes between sand, silt, and clay particles in terms of. But what I want to point out to you chemically is that silt and sand particles essentially have no embedded charge in them. Is there a little bit of charge that they come with? Yes, but it's so small that we can essentially ignore it. Clay particles, however, are sufficiently small with enough surface area that the embedded charge there actually is appreciable. And because they have this appreciable charge in them, therefore, it can interact chemically with ions, something that sands and silts and larger particle sizes can't do. So let's ignore sand and silt because they essentially don't function chemically. And let's just look at the clay fraction. All right, so now we're just looking at that clay fraction. And just like we said before, there's certain types of clays that are positively charged, iron and aluminum oxides, and there are certain types of clays that are negatively charged, smectites, kaolinites, and there are plenty of others. I have certainly not listed them all. I've given you very ballpark ideas for the relative charge of these different types of clays. Now, one thing we could note is that organic matter itself comes with charge, comes with a lot of embedded negative charge. Instead of 8 centimoles of charge per kilogram, as with smectites, for organic matter, we're talking more like negative 200 centimoles of charge per kilogram. So if you want to know what's the true powerhouse in the room as far as chemical activity goes, well, it's really going to be organic. Okay. Now, if we've got positive charges, what does that mean? If we've got negative charges, what does that mean? Well, if we've got positive charges, that means that we can attract negative things. And if we've got negative charges, well, then we can attract positive things. So this is something that clays can do. This is something organic matter can do, but it's not something that silt or sand or rocks can do. So if we think about it a little bit more, soils with organic matter and clay are going to be better at retaining cations. Soils with more iron and aluminum oxides will be better at retaining negatively charged things like phosphate or nitrate. Now, ammonium has a charge of 1 and nitrate has a charge of 1. The one is positive, the other is negative. But, um, but because this is something new, but it's to keep in mind, the soils that we're going to be observing on the eastern shore are going to be higher in clay than are in oxide content. So what that means is that the soils that we're going to be observing generally have more negative charge associated with them than positive charge. So soils on the eastern shore are going to be able to retain more cations than anions. And because of this, even though ammonium and nitrate have the same magnitude of charge, soils on the eastern shore are going to be capable of retaining more ammonium than they are nitrate. And that's one of the reasons why we think of nitrate as being so soluble, because it is it attracted to the iron, to a portion of the soils that we have? Yes, but there's not a lot of stuff in there that can attract them because we don't have that many iron and aluminum oxides in eastern shore soils generally. So the ability to retain those negative ions is limited. And nitrate, having only a charge of -1, can't be those positives as much as a phosphate can, which has a much higher negative charge. So that's why nitrate tends to leach so much. And Sarah Hirsch tomorrow is going to be with us to talk a little bit about that, which I'm looking forward to so much. So you can see that phosphate's going to be retained a little bit harder than nitrate is. And this brings up an interesting question. If phosphate is so highly charged and therefore sticks to soil so strong, why is there ever a danger of phosphorus leach, even when erosion is zero, right? If phosphorus is stuck to soil, well, of course we can lose it by erosion. But what if we've minimized erosion? How could phosphorus possibly leach if it's to soil so strongly? Remember what phosphorus sticks to. It sticks to positives. And what it's sticking to is it's sticking to iron and aluminum. But soils on the eastern shore don't have a lot. of iron and aluminum. And at some point, we can have enough phosphorus there that all of the spots in the iron and aluminum that are available for something negative like phosphorus to stick to, all those spots get used up. And if we add any more phosphorus, there's simply no room for it to be absorbed. What we observe in real life in the laboratory is if we take a soil um, and add phosphorus-laden water to it, okay, we can shake it around. And if the phosphorus in the water that we've isn't that much, such that it hasn't overwhelmed the iron and aluminum that's in that soil, then not a lot of that phosphorus in the water that we've added becomes soluble or stays soluble. But at some point, if we add enough phosphorus and saturate that iron and aluminum, then there's simply no more places for that phosphorus to stick. And so the phosphorus becomes much more soluble. So we kind of get this kind of bent stick behavior above a certain threshold. Uh, Phosphorus becomes much more soluble than it was before. So index that we can use to judge this degree of saturation of the soil. Well, it's a simple ratio of the number of atoms of phosphorus divided by the number of atoms of iron and aluminum, the stuff that the phosphorus can stick to. All right, and there's different ways to calculate DPS, but generally somewhere between 15 and 30% of a degree of phosphorus saturation, we're going to see that the bend in that stick occur. We're going to see phosphorus become more soluble than before. All right, here's another reason why soil texture matters. Soil texture matters because it decides hydrology. And how it decides hydrology depends on how wet the soil already is. Okay? Keep in mind, because the payoff here is kind of interesting. All right, and if we've got enough time, we'll watch a little video that's about soil texture and hydrology. Now, if soil is saturated, well, the downward rate of water through the soil is really dictated by the most limiting horizon. The most limiting horizon really forms a bottleneck in the ability of water to descend through the whole profile. It just kind of makes sense. But what if the soil is not saturated? The downward rate of water movement is the function of the soil moisture that's in the horizon that the soil is in right now as it descends, and the average size of pores in that. All right? Let's think about pore size for a second. The larger the pore size is, the larger the pore size, the smaller the amount of surface area that's presented to water. And what that means is that there's less for the water to cling to. That's for a larger pore size. So big pores in the soil mean the water has less to cling to, and so the water is less attracted to the soil material. If we've got really small pores in the soil, well, then the water is always right next to the surface, and so there's greater attraction. And so the water is more strongly attracted to that soil. Another thing to keep in mind is that the stronger the remaining water that's there clings to it. If I've got a saturated soil, a certain amount of water will just drip out. Once that soil dries out enough, the remaining water stays. So two things here to keep in mind. The downward rate of water movement is a function of how dry is that soil already. If the soil is relatively dry, then the remaining water is stuck more strongly. And then how big are the soil pores? If the soil pores are big, well, then that means the water is less attracted, but if the soil pores are small, the water is even more attracted. Let's think about what that means, all right? Let's think of a sand overlying a, all right? So let's say we've got sand overlying a clay, and we've got water moving from the sandy layer, and it hits that clay layer. What's going to happen? Well, the water in the sand, as it hits that clay, it's going to see those smaller pores, and it's immediately going to want to go in because it's attracted to those smaller pores, right? But of course, even though it immediately goes in, it's getting into a thing that has smaller pores, so it won't be able to descend through the clay nearly as fast as it descended through the sand. What about the opposite case, where we've got a clayey horizon overlying a sand? Well, that water in that clay horizon, it's going to see that sandy layer, but it's going to see those big pores, and it's not going to want to enter immediately because it has no attraction to those big pores. The only way that it's going to go into the sand below is if the clay layer is becomes saturated so that that additional water isn't attracted to those clays anymore. And so it'll go into the sand because it's no longer attracted to the clay. We're going to watch a video about that shortly. So we're going to watch a video so you can see this, but here's the bottom line. When the soil is not saturated, regardless of the situation, a texture change slows water movement down the profile. Doesn't matter whether you're going from sand to clay or clay to sand. A texture change slows water movement if you're not starting off with the soil that's originally saturated. What does that mean? The slowing of water movement at a textural boundary, deposit materials, think of that as clay. Think of that as iron and aluminum oxides, or organic matter, or think of that as ions, right? The slowing of water movement at textural boundaries can deposit materials, and that affects soil development and nutrient retention. So oftentimes when we start to develop new horizons, they start to develop at a textural. And oftentimes if we're going to be retaining ions, we'll be retaining them at a textural boundary. Isn't that neat? All right. It's all because of soil texture. Now, if some of this seems a little mystifying, or you want some proof, then what I'm going to do now, I'm going to go to the internet, and I'm going to, just like it says in the packet that I've given you, I'm going to go to YouTube, and I'm going to search water. There it is, water movement in the soil. All right. And what I'm going to do is I'm going to look for the version that has been posted by this guy, Rick Rupp. All right. No relation. Okay. This is a really old. In fact, it's a little too old school, which you'll observe if you watch the thing all the way through. But what I'd like us to do is spend our remaining time beginning at minute 3 minutes and 40 seconds, all the way to minute 9. And you'll get to see what I'm talking about how much a textural boundary can mean to soil development. Now, when I start this video at 3 minutes, or when you can start the video at 3 minutes and 40 seconds and actually see for yourself. And you don't need me to narrate it. In fact, you should kind of turn me off as far as the headphones go, and you should just listen to the video. But you'll be able to kind of literally see how when a sandy layer overlying a clay layer, the water will enter the clay layer but move very slowly through it. Whereas if you have a clay layer entering sand, it will stop at the sand layer and only enter after the clay layer has become saturated. In other words, when the soil is not saturated originally, a change slows the movement of water down the profile. This is the end of our webinar. What I want you to do now is go to YouTube, type in water movement in the soil, click on the version by Rick Rupp, and you can start looking for at the very beginning if you want. The good stuff really begins to happen at minute 3:40. All right? Thank you all very much for joining.
Are there any last questions before I end the recording? Now you can type in the chat or speak up. And of course, send emails once I close it, things like that, if anything else pops into mind. Thanks for coming.